This is screencast number 2 for acid-base titrations. This time we're going to look at a weak acid being titrated with a strong base. So the pH is not going to be at the equivalence point. And if we think about what we learned in first year chemistry when we had a weak acid with a strong base, a lot of you predicted that the pH at the equivalence point would be greater than 7. And that is absolutely correct, but you were probably predicting it because of this, right? And we talked about the fact that it really has nothing to do with the fact that you have a strong base. It has everything to do with the weak acid, and specifically the conjugate base of the weak acid, because that guy is going to undergo hydrolysis at the equivalence point. And so this is an example of where you can get the right answer. You arrive at it basically for the wrong reasons, but it certainly helps you to predict. So when you see a titration curve like this, and again, the easiest way to find the equivalence point is kind of to find that steep vertical climb and pick the halfway point. So if you look at this one, the equivalence point is certainly greater than 7, right? So even if they hadn't told you what they were titrating it with, you should be able to predict when you see this, that's a strong base. And so because the pH is greater than 7 at the equivalence point, you know that this is a weak acid that it's being titrated with. Okay? So we're going to do the same thing we did with the strong acid, strong base case, but now with a weak acid. And you're going to see that it's much more involved. It's not just a stoichiometry problem. But basically, every time you are adding an acid or a base, depending on which scenario, we're in scenario 2 right now, so I'm kind of getting ahead of myself to scenario 3, but you disturb the equilibrium. So when you disturb the equilibrium, because some of that acid is being used to neutralize the sodium hydroxide, it's going to adjust and get back to equilibrium. So we're basically going to do an ice table so that we can keep an account of who's in excess, similar to what we did with the strong acid, strong base. And then the second step is going to be to use the Henderson-Hasselbalch equation to see how it adjusts back to equilibrium and what the pH will be. Again, we've got to watch for additive volumes because the concentrations are going to be more dilute because you've added to the original concentrations. Those are all things we want to think about. Okay, so they've given me the Ka for this weak acid, and they want to know basically what is the starting pH. So the easiest way to do that is certainly you could do an ice table if you wanted to. Right? So we know that if the concentration is 0.200 molar, these are zeros, these will go up by x, minus x. That K is small enough that we can assume that x is fairly small, so we don't need to worry about subtracting it. And so we say 1.8 times 10 to the negative 4th is x squared over 0.2. X is the H plus, and that comes out to 0.0060 molar. So pH is just negative log of that. And we get a starting pH of 2.22, which please stop and ask yourself, does that make sense? It's a weak acid, pH should be less than 7. So if we'd gotten something like 10, then we would know, oops, we must have a POH instead. So our starting pH is 2.22, which is reasonable. Now you absolutely could have, let's see. Okay, sorry, lost my train of thought. Starting pH is 2.22. So now we're basically gonna stress it. We're gonna add some base, and the acid's gonna neutralize that base. So let's get our ice table set up. You're adding sodium hydroxide, but we don't so much care about sodium. We care about the hydroxide. This reaction is going to go to completion, and so that's going to make, this H is going to come off and make water, and then we've got the conjugate base that's left. Okay, so my suggestion when you do the ice table is to use moles. And the reason you want to use moles is because we're diluting, and so if we try to work in molarities, it's going to be getting it into molarity and out of a molarity, and it's going to be a whole pain. And then the last step is to use the Henderson-Hasselbalch equation. to figure out what the pH is. So I'll show you what I mean by that. Okay, so let's figure out the millimoles that we have of acid. So the concentration is 0.200 and the volume is 50 milliliters. And so our millimoles of acid is equal to 10 millimoles. So that's going to be our starting for all these ice tables. And then millimoles of base, it's 0.4 molar. And for this part, we've added 5 milliliters. So I want to do that each time so that we know what our starting is. So 2.00 millimoles. All right. 00. So again, it's a similar picture to what we have with the strong acid, strong base, but we've got to do it in an ice table because it's not a strong acid or a strong base that fully dissociates. We can't assume that whatever we have left of this is going to all form that, right? Doesn't work that way. So we assume that all this is neutralized. So that means this, starting at 0, will go up by 2, right? So now I have 8 millimoles of acid left, I have no hydroxide left, and I have 2 millimoles of conjugate base left. Okay. Now, we can throw it into the Henderson-Hasselbalch equation, but we got to be careful because these are moles, right, at equilibrium, and our total volume is now 50 plus 55. So what I want to do is come in and divide these by 55, divide by 55 to turn them into concentrations. By doing that, I'm making sure I'm diluting it, and I can go in and I can plug these in to the Henderson-Hasselbalch equation. So when we do 8 over 55, we get 0.145 molar, and when we do 2 over 55, we get 0.0364 molar. Now you can certainly do a second ice table like we did up here, right? And so instead of this being starting at 0, it would be starting at 0.0364, and you would be solving for H+. But usually at this point students like to go ahead and just throw it into the Henderson-Hasselbalch, but you're welcome to do that second ice table. So negative log of 1.8 times 10 to the negative 4 plus the log of our base over our acid. So our base, our conjugate base, is the 0.0364. So that'll go on top, and on bottom will go the acid, so the 0.145. So pH is equal to 3.14. Alright, so our starting pH was 2.22, which is reasonable for a weak acid. We added some strong base to it, and it jumped up to 3.14. So it makes sense because the pH is climbing, but we've just added that small amount of base, so not a huge deal. Alright, so now we're going to add 12.5 milliliters of our strong base. So same ice table. Just like the strong case, we go back to our original starting condition, so we still have 10 millimoles of our acid, and now I need to figure out, well, how many millimoles of base do I have? So 12.5 milliliters times the concentration of the base was 0.400, so millimoles of base is equal to 5 millimoles. Alright, so our acid is still in excess, so that whole 5 is going to get used up, so that means 5 of the acid will be left. The base is going to be gone. This was 0 to begin with, it goes up by 5. So we have 5 millimoles of the conjugate, we have 5 millimoles of the base, and we're at a special point here. We're at the midpoint. And the midpoint is halfway to the equivalence point. And if you think about what's going to happen when we plug it into the Henderson-Hasselbalch equation, this concentration of conjugate base is going to be equal to the concentration of the acid. And so if you think about the Henderson-Hasselbalch, if it's taking the log of 1, that's just 0. So pH is just going to be equal to the pKa because this whole term falls out. Now, if you forget that, it's not the end of the world, right? But that will always be true anytime you're at the midpoint, so you've neutralized half of your acid or your base, then pH will be equal to the pKa. So pH is negative log of 1.8 times 10 to the negative 4, and so we get a pH of 3.74. So again, stop and ask yourself, does that make sense? We added some base, the pH climbed from 3.14 to 3.74. So we're in good shape there. All right. So part D, we're adding 24.50 milliliters. So millimoles of base, 24.50 times the 0.4. So the millimoles of base that's been added now is 9.80. So we're getting close to equivalence point. So here's my ice table. And really this ice table is not like an equilibrium table. You notice that we're doing the one direction, right? Because this goes to completion. As long as the strong is in excess, then we really don't have an equilibrium until we get to that second. Alright, so all 9.80 is going to be used. So we have 0 of that. We have very little of our acid left, but in the process we generate 9.80 of our conjugate base. So we've got our moles. I'm going to divide by the total volume. So 24.50 plus the original 50 milliliters, we divide by 74.5 milliliters. 74.5 milliliters. And so our concentration of acid is small, 2.68 times 10 to the negative third, and our concentration of conjugate base is 0.132. Molar. So to get the pH, negative log of the Ka plus the log, the base is going to go on top, so the 0.132 goes on top. The 2.68 times 10 to the negative third goes on the bottom. So we get a pH of 5.44. Again, we're not quite at the equivalence point because these guys aren't equal, but we've certainly climbed, right? And so on our titration curve, we have increased, and we're getting to the point where we're about to shoot up to the equivalence point. Alright, so now we've added 25 milliliters of base. That's going to be a special point for us. So 0.400 times 25 milliliters. So now we've added 10 millimoles of base. So we know we had 10 millimoles of acid to begin with, right? So all the acid is gone, all the base is gone, and in the process, what did we create? Well, we created 10 millimoles of conjugate base, and the total volume is 75 milliliters. So the concentration of the conjugate base is just the millimoles over the milliliters. So that comes out to 0.133 molar. Alright, so we are at the equivalence point. If this was a strong acid, strong base, we'd call it a day and say, hey, the pH is 7. We know that's not going to be the case. And the reason is not because of the strong base, but because of this conjugate base. What is this conjugate base going to do? He's going to undergo hydrolysis. And if you guys will actually like narrate as you're doing these problems, that will help you understand really what's going on at the equivalence point. So this conjugate base, this COOH minus, when he undergoes hydrolysis, he takes on an H, because that's what bases do. And so what will be left of the water if he does that is an OH minus. So this is the reason we're going to be basic at the equivalence point. It has nothing to do with the strong base that we're being added. That's because this guy's going to undergo hydrolysis. So the starting concentration is 0.133. These guys are 0. These are going to go up by x, down by x. 0.133 minus x, and x. And we'll pick up in the next screencast.